Hello, ladies. Let's go ahead and get these last three gas law problems out of the way. Okay, so the next question said a large evacuated disk has initially a mass of 134 grams at mass. And sorry about that. Let me go and fix my pen because I have to turn on the pen for me to actually write. There we go. So we have a mass of 134.567 grams. When the flask is filled with a gas of unknown molar mass, right? So that's what we're looking for right here. Unknown molar mass. That's what we're looking for right here. All right. That's the question mark. It has a pressure of 735 torr and then 31 degrees Celsius. Okay. Its mass when it's inside, and its mass is 137.456. Okay. About what 3 grams heavier. Okay. So the flask is evacuated again, and then it's filled with water that is at 31 degrees Celsius, just like this one is, right? And they're doing this so that they can figure out the volume of the flask is. And we can use the grams of water in there, right, to figure out what the volume of the actual flask is, okay? And it gives you that the density of water is 0.997 grams per mil, which is helpful, okay? Assuming ideal gas equation applies, right, not Van der Waals equation, but ideal gas equation applies, this is one of those PV equals under T things again, but it's going to be a modification on that, right? So the first thing I would do is go over here to the 135 torr, right? And I would convert that to ATM because it needs to be in ATM. And when you convert that to ATM, it is 0.967 ATM. All right. And if you don't know how to convert it, it's actually in the notes. And you can just do dimensional analysis to convert it. And then let's do the same thing again with this here, the 31 degrees Celsius. This in Kelvin is 304 degrees Kelvin. Okay, so those numbers are going to be needed later. Okay, those numbers are going to be needed later. All right, so first thing to do here, right, is we've got to figure out what the volume of the gas is. Okay, because you need that for the rest of the equation, right? We can do that by using the total volume right here of the flask and subtracting from it the mass of the flask when it's empty. Okay, and so oh yeah, this by the way, this is the total volume of the flask with the water in it. Okay, because if you subtract the mass of the flask when it's empty from the volume from the mass of the flask with the water, then all you're left with is the mass of the water, right? So that's going to be 1067 grams. Sorry, it's actually 1067.9 grams. Okay, subtracted by subtracted from it. I already forgot the number. There it is. It's up there. 134.567 grams. Okay, 134.567 grams. And then that equals, do it in your calculator real quick, it is 933.3 grams. Okay, you remember from the very first lecture we had, density equals mass divided by volume. And so you move things around so that you have volume equals then mass divided by density. And so all you have to do now is take the mass of the water that you have here, which is 933.3 grams, divided by the density of the water, which is given to us right here, 0.997 grams per mil. We can cancel out those grams and we're left with a volume. And that volume should be 936 mils. Or remember, everything needs to be converted to liters. When it's converted to liters, it's 0.936 liters, or 0.936 liters, right? And remember, this is the volume of the unknown gas in the flask, okay? Good, good. Now we have to figure out the mass of the gas. We can do that the same way again, where we have the mass of the flask with the gas in it, which is 137.56456, and then we have the mass of the flask without anything in it at all. Subtract those two now. So that's 137.456 grams subtracted by the mass of the flask by itself, 134.567, and that gives us 2.889 grams. Okay, so that's the mass of the flask. I mean, sorry, the mass of the gas. All right, mass of the gas. Okay, cool, cool. Now that we have the mass of the gas and we have the volume of the gas, we can figure out what the density of the gas is. So D equals M over V, which means then we do 2.889 grams, all divided by 0.936 liters. And that gives us a density of gas being 3.09 grams per liter. Awesome, awesome. And you know why this is awesome? Because we have this density of the gas. It's awesome because we have an equation that I gave you in the notes that says that the molar mass, which is big M, right, equals the density times the ideal gas constant times T divided by P, right? So you can get the molar mass. So plug and chug, as Catherine likes to say it. We have 3.09 grams liters times the ideal gas constant, which is 0.08206, and that unit is ATM, liters ATM, all over moles Kelvin. All right, and that is multiplied now by the temperature, which is 304 Kelvin from before, right, from up here. And all of that now is divided by 0.967 ATM, which was the pressure we calculated earlier, right, from torr. And so all that done in the calculator should give you 79.7 grams per mole, and that should be your the molar mass of your unknown mass. I mean unknown gas. There we go. Unknown gas molecular mass equals 79.7 grams per mole. Make sure we have the right number of sig figs here. Looks like the smallest number of sig figs we have is actually the 31 degrees right there, right? But we converted that to 304, right? We converted to 304, so I mean I would accept either here. It could either be 2 sig figs or 3 sig figs. Either one could be fine, and so we'll leave it at 3 sig figs. But if you wanted to make it 2 sig figs, it would just be 80 grams per mole. Simple as that. All right. The second to last question, which is, I believe, yes, this one right here. An automobile airbag is inflated by nitrogen gas generated by the rapid decomposition of sodium azide, Na, N3. And again, I'm so nice because I provided you with a balanced chemical equation. There are 2 moles of sodium azide for every 1 mole of sodium and every 3 moles of nitrogen gas, right? So if the airbag has a volume of 36 liters It is to be filled with nitrogen gas at 1.15 atm at 26 degrees Celsius. How many grams should be of the sodium azide must decompose to get you that amount of gas to save your life when you collide with something, your airbag goes off, right? So again, this is another PV equals nRT type of thing, right? So I would just go ahead and convert that to Kelvin, which should be 299 Kelvin, right? And so with PV equals nRT, we'll rearrange it so that we get number of moles by itself. So N equals PV over RT. And so now the equation should be 1.15 ATM times 36 liters from the 36 liters right here. Right? All that divided by ideal gas constant 0.08206 liters ATM mole Kelvin. Right? All that multiplied by the temperature, 299 Kelvin, that we calculated or converted right there. Right? You do that math, and you should get 1.7 moles of nitrogen gas. Okay, nitrogen gas. I don't know why I wrote it that way. It should be into gas. There we go. So that's great. That's great. But the problem, though, is the question's asking for how many grams of sodium azide must be there to make that much gas. So we have to do our stoichiometry now. So if you look at your balanced chemical equation, for every 2 moles of sodium, right? Or sorry, not sodium. 2 moles of 3 moles for every 3 moles of nitrogen gas, we get 2 moles of sodium azide. So we put down here 2 moles of 3 moles. 3 moles of nitrogen gas. And for every 3 moles of nitrogen gas, we get 2 moles of sodium azide. Okay. And then we get for every 1 mole of sodium azide, we get the molecular weight of sodium azide, which I calculate to be 65.0 grams sodium azide. Great, because now we can cancel out moles of gas, moles of sodium azide, and we're left with just grams of azide. So that should give you equals 72 grams of sodium azide, right? And so the one with the smallest number of significant figures here, the temperature, again, here's a liters that has 2 significant figures, so we should use that. So 72 grams has 2 significant figures, perfect. All right, this one had 2 sig figs too. Okay. Good stuff, good stuff, good stuff. Good and easy stuff. All right. Our last problem is going to be a combination of PV equals nRT, which is ideal gas law, and Dalton's partial pressure law, where the total pressure equals the sum of all the pressures of the partial pressures of each gas. So when you look at this particular problem here, it says that there's a mixture of 6 grams of oxygen and 9 grams of methane, right? And so the mixture of your gases here is a mixture of methane and oxygen, right? You have 6 grams of oxygen, 9 grams of methane. You put it all into a 15-liter flask at freezing temperature, right? 0 degrees Celsius. What is the partial pressure of each gas? And what is the total pressure in the entire vessel, right? So the partial pressure of each gas, that's the one where you use PV equals nRT and some stoichiometry. And then the total pressure of each gas, the total pressure in the vessel will be the Dalton's partial pressure law, okay? So let's start out by doing the stoichiometry required to get to the moles of oxygen and the moles of methane, right? So we need, from here, we need moles of oxygen, because you can't do anything with grams unless it specifically asks for that, right? And then we need to convert do the stoichiometry to make the 9 grams of methane to moles of methane. Right, so it's just like every other molar calculation slash, not molar calculation, but stoichiometry, dimensional analysis calculation we've ever done. So the number of moles, which is N, of oxygen, or O2 gas, is equal to the 6 grams, 6.00 grams of O2, right? For every 1 mole of O2, you get 32 grams of O2. That's simple. Divide 6 by 32, you should get 0.1880 moles of O2. That's good. Okay, so number of moles of CH4 or methane. So same thing again, except this time we're using methane. 9.00 grams of methane for every 1 mole of methane. You get its weight, which is, molecular weight is 16 grams of methane. It's as easy as dividing 9 by 16, and that gives us 0.563 about moles of methane. See, so far so good, right? So now that you have moles of oxygen and you have moles of methane, you could use that with PV equals nRT to figure out what the pressure of methane is, because I gave you a temperature here, right, and a volume, right? So let's do the pressure of oxygen first. PO2, right, pressure of oxygen, okay, and that equals then again, this is just PV equals nRT, right, and all I've done is, again, this is PV equals nRT, and I've just rearranged the equation so that P is by itself, and I can solve for everything else, solve for P using everything else. So that equals then the partial pressure of oxygen equals the number of moles of oxygen times the ideal gas constant times the temperature divided by the volume, right? And again, as Catherine always says, plug and chug time. We put the 0.1880 right here, moles, right? That came from our previous calculation, right there. Multiply that by the ideal gas constant, 0.08206, and the unit there is liters ATM slash mole Kelvin, right? And then you multiply that by the temperature. And again, I would just do this from the very beginning, right? Convert that 0 degrees Celsius to Kelvin, and that's going to be 273 Kelvin. And so you times it by 273 Kelvin. All that divided by the volume, which is 15 liters, right? Or 15.0 liters. Okay, cool. So this should give you then the answer to that. The partial pressure of oxygen should be 0.281 ATM. So let's do the same thing again now for the partial pressure of methane. So that equals the number of moles of methane times the ideal gas constant times the temperature, all divided by the volume. Right? Same thing again, except this time we're going to use the moles from methane. Okay? So 0.563 moles. All that times the ideal gas constant, 0.08206, right? Liters ATM mole Kelvin. All that multiplied by the temperature, which is 273 K. And then we can divide all that by the volume, the same volume from above. That's 15.0 liters. And so that should give you then a partial pressure of methane, right, equals, after you do that math, 0.841 ATM. Okay? So now that you've got the partial pressure for methane, and the partial pressure for oxygen, you can figure out what the total pressure of the vessel is. Because remember, Dalton's partial pressure law says that the total pressure of a vessel equals the partial pressure the sum of all the partial pressures of all the individual gases. So in this case, it'd be the partial pressure of oxygen plus the partial pressure of methane. All right, so then that equals 0.281 atm from oxygen plus 0.841 atm from the methane. And so that gives you then if you add the two together, you get 1.122 atms as your total pressure. And if we look at if we look up here and see what the smallest number of significant figures is this one right here. The 0 has one significant figure. Okay. I mean, the 0 by itself is not really significant, but I mean, that's the lowest you can go, right? So we'll say that the answer here then is actually 1 atm. Okay. Fun stuff. And that's how you do those problems. So if you guys have any questions, let me know. DM me on the Teams, or you can email me. I'll be around. Otherwise, I'll see you on Monday. Remember that your test over thermochemistry and gas laws is on Tuesday. Good luck. Bye.